Okay, so we started with the applications of binary tree, and there we have seen that the two major applications of binary tree are expression trees and Huffman encoding. Okay, and then we started with the expression tree, and we have seen that what do you mean by an expression tree? An expression tree is a binary tree in which each internal node corresponds to operator and each leaf node corresponds to operand. Okay, so there we have seen basically how we use an expression to create an expression tree, and once we create an expression tree, so different traversal of that expression tree will give us different type of expression. In order traversal will give us in order expression, reorder traversal will give us reorder expression, and post order traversal will give us post order expression. Okay, so we started with expression tree. We have seen the algorithm for the expression tree. So this is the algorithm which we have followed, and then we have finally created a expression for the given postfix expression. Sorry, I got disconnected. So we have taken a given postfix expression, and then out of the given postfix expression, with the help of stack, we have created this expression tree. Okay, so that was about expression tree, and then the next application, important application, is a Huffman encoding technique, or simply an Huffman encoding algorithm. So this is the second most important application of a binary tree, and today we'll talk about this second application, that is Huffman encoding. So let us try to understand first of all what is Huffman encoding, and once we do that, then we'll take an example to apply the Huffman encoding, and we'll see what is the outcome of Huffman encoding algorithm. So Huffman encoding, the first important thing about Huffman encoding is that Huffman encoding is a lossless data compression algorithm. Okay. Now here you need to understand two important things. First important thing is what? It's a data compression algorithm. I repeat, it's a data compression algorithm. Second important thing it is that it is a lossless data compression algorithm. Now, when you talk about a data compression algorithm, you must be knowing that when you have a bigger file and you want to reduce the size of a bigger file without changing the content of the file or without affecting the content of the file, so we make use of compression software, something like your WinZip or the RAR or anything like that. Okay, so what those software do, they make use of compression algorithms or the different compression techniques, and then they try to reduce the space requirement of the data. I repeat, they try to reduce the space requirement of the data. That is called the compression algorithm or the compression technique, or in general data compression technique. Now, under data compression technique, there are two possibilities, or rather, there are two categories. One is your uh, lossless, and another is called your lossy. Okay, so in lossy data compression algorithm, there is a loss of a data. So the integrity, or you can say the originality of the data is not maintained. So when you decompress the data or when you decode the data, at that time there is some loss of the data in lossy data compression algorithm. But in lossless data compression algorithms, this doesn't happen. So whatever is the original data, after encoding, we get some text. We call it ciphertext, and then after decoding, we get the original data, which is exactly similar to the original data at the source side before compression. So there is no loss at all. And such techniques or such algorithms are called as lossless data compression algorithms. Okay, and Huffman encoding is one of such lossless data compression algorithms. Okay, so very important point about Huffman, that it is a lossless data compression algorithm. Then what do we do in Huffman encoding? A variable length code is assigned to input different characters. Okay. Now, when we apply the Huffman algorithm, or basically when we apply any compression algorithm, so we take an example of a single word, or say 2-word example or 3-word example. So the way we apply the algorithm for the single word, or say for 2-word, the same way we apply that algorithm for the entire text of a file. So that text can be, say, of 100 words, can be of 500 words, can be of multiple pages, and so on. Okay, because at the end of a day, we need to understand that whatever is the size of your file, your textual file basically consists of characters. Okay, so the most important thing is our character. Fine. How many characters you have, that is not that much important. The important thing is how do we represent the character, and that representation of the character defines the size. I repeat, the representation of the character defines the size. Okay. So what happens in Huffman encoding technique? A variable length code is assigned to input different characters. So for different character, you have different length code. I repeat, for different characters, you have different length codes. Okay, that we'll see in the example. Next is the code length. Now the second point says what? A variable length code is assigned to different characters. Okay. Now when we say variable length code, so basically that varying length of a code should be dependent on something. For example, for character A, if I am giving a code of length 3, and for character B, if I am giving a code of length 4, and then for character C, I am giving a code of length 2. Okay, 2 bits, I mean to say. Code of length 2 means 2 bits. So for C, I am giving a code of 2 bits. For B, I am giving a code of 4 bits. And for A, I am giving a code of 3 bits. So this length, this varying length, 3 bits, 4 bits, and 2 bits, this length should be dependent on something. There should be some logic behind this varying length. Okay. So the logic in Huffman algorithm for this varying length is dependent, or it is related to the frequency. I repeat, it is related to the frequency of the occurrence of the character. It is related to the frequency of the occurrence of the character. How many times a specific character is occurring in a given word, or a given sentence, or a given file. Okay. How many times a specific character is occurring in a given word, or a given sentence, or a given file. Okay. That number of times is called frequency of that character. What it is called? Frequency of a character. So the code length is related to how frequently characters are used. This is what being said in this third sentence. The code length is related to how frequently characters are used. So for example, if a sentence is given to me for compression, or a single word is given to me for compression, so I would be checking that how many times a specific character is occurring into that specific word, or a given word. Okay, so that becomes the frequency of that character. Depending upon the frequency of the character, we will be generating a varying length code for that character. Okay, how we will be generating? That's your Huffman encoding algorithm. Next point, most frequent characters, and this is one of the most important points. Most frequent characters have the smallest codes, and longer codes are assigned to least frequent characters. It simply means that the characters which is having more frequency will be assigned with smaller code, and the characters with lesser frequency will be assigned with bigger code or the longer code. Okay, so the character which is occurring again and again, which is happening again and again, that character will be having smaller code, and the character which is having lesser frequency, so it is not frequently occurring, so that character will be given longer code. Okay, there are two important parts for the Huffman encoding algorithm. The first important part is to create a Huffman tree out of the given data, and second important part is to traverse the tree to find or to assign the codes. Okay, so first of all, we create a Huffman tree, the first part of the algorithm. Once the Huffman tree is created, then the second part is what? The second part is to assign or find the codes. Okay, now in the second part, basically we will be finding the code from the Huffman tree itself. How? By traversing the Huffman tree. Okay, so let's see that. Now, this is the example which we are going to solve now. So use Huffman coding and generate codes for. Now generate codes for. Now we are given with a data, and that data is data structure. So this is the data which is input to us, and what we need to do, we need to find, or we need to generate the varying length code for all the characters, for all the unique characters in the given data. So this becomes an input, or rather this is the input for our algorithm data structure. This input can be a single word, this input can be a multi-word, this input can be a sentence, this input can be a paragraph, this input can be a file. Okay, it is as simple as that. But whenever we solve the example, we go with the simplest example, or we go with the simplest input, so that all can understand it better. Okay, I repeat, this input can be a single word, can be multi-word, can be an entire file consisting of many words. Okay, the algorithm would remain same, the logic would remain same. So for what we need to do, first of all, we need to create a table like this, and this table is a part of solution. In the question, you have a single line, that first line, use Huffman coding and generate codes for. Okay, then the data is given to you, data structure, or say the input is madam, or say the input is Malayalam, or the input is computer, or the input is computer space engineering. You need to ignore space. Okay, white spaces should be ignored. So now, first of all, we'll be creating this table. The table which is having the first column as serial number, then the second column as symbol or character, the third column is the frequency of that character, fourth column is fixed length code, and then finally the fifth column is variable length code, which we need to find out using the Huffman encoding algorithm. So the first character is this D. So the D becomes our first character, and then we find the frequency. How do we find the frequency? How many times D is present in this given input? That becomes my frequency. Okay, so D is occurring only once, so I am writing it as 1. The frequency of D becomes 1. Then the second character is A. Okay, we will be reading the string from left to right. So I am starting from this D, and then I am going up to E. Okay, this way. So first is D. D is occurring only once, so the frequency is 1. Second is A. A is occurring twice, 1 and then 2. Okay, so the frequency of A over here is 2. Then likewise, the next character is T. After A, we have T. The frequency of T is 1 over here, then 2, and then here it is 3. Okay, so the frequency of T becomes 3. So the frequency of T becomes 3. Okay, then the next character is S. Unique characters we are talking about. So after T, we have A over here. but that A has been counted, has been considered. So the next is S. Okay, so we'll be seeing S, then the frequency of S 1, then R, frequency of R is 2, then U, frequency of U is 2, then C, frequency of C is 1, and then E, the frequency of E is 1 again. Okay, once this is done, what we need to do, we need to sum up these frequencies. We need to sum up these frequencies, and we need to write the total of this sum up, and that total is coming out to be 13. Now you need to compare this 13 with the number of characters in the given input. The given input is data structure. Please count the number of characters, total number of characters. So DATA 4, then space, just ignore it, then STRUCTURE. Okay, so here you have total 9 characters. So 9 plus 4 is 13. So this frequency is also 13. You always need to first of all cross check this. If you are making a mistake over here, means you have counted any character frequency wrong. If that is wrong, then the entire algorithm will go wrong. Okay, so the first check should be, after your frequencies has been done over here, check the total of the frequency and compare it with the total number of characters. That is the first thing you need to do. If that is matching, then you need to proceed next. Then the next column is this fixed length code. Now what is this fixed length code? As the name suggests, the length of the code is fixed. The length of the code is fixed. And suppose I am taking 8 bits for one character, which is minimum. So I will be taking 1 byte for one character, or 8 bits for one character. So that way, if I encode this character, so D is for having a D is having, for example, the code of all zeros, then A is having code of all 0, then 1, then likewise. So 0 0 0 0, then 0 0 0 0 0 0 0 1, and likewise for T, and so on. So the fixed length codes are assigned in sequence, simply in sequence. And then if we find out the total, so one character is taking your how many? 8 bits. So total your 8 characters will take 64 bits, and this is only 8 characters. But the total number of characters in this given input is 13. So the space requirement of the given input data structure is 13 into 8. I repeat, the space requirement of data structure is 13 into 8. Okay, so that will be the total number of bits required for the given input data structure. Now once that is done, so the next is variable length code. And to find this variable length code, we need to first of all create a Huffman tree. And once we create the Huffman tree, then we need to traverse the Huffman tree to find the variable length code for all the unique characters. Okay, so let's proceed for that. This is the given question. Use Huffman coding and generate codes for data structure. Now, what do we do in Huffman algorithm? In every step of the Huffman algorithm, we will be arranging the characters in the ascending order of their frequencies. I repeat, we will be arranging the characters in the ascending order of their frequencies. So what I am doing here, now here I am not at all writing the character. Instead, I am simply writing their frequencies in the ascending order. Okay, so if I go back, so here onto this screen, what we can see, let me, what we can see that these are the frequencies of our character. Fine. And we have total 8 unique characters. So what we need to do in the first step and in every step, we need to arrange these characters in the ascending order of their frequencies. So when I say in the ascending order of the frequencies, so how we will be arranging the characters? If I talk about character frequencies, then it is 1, 1, 1, 1, 4 ones are there, then 2, 2, 2, 3 twos are there, and then finally 3. Total 8 characters, okay, or 8 frequencies. The first 4 frequencies are 1, 1, 1, 1, and then you have 2, 2, total, 1 minute, sorry, 4 ones are there. 4 ones are there, and then 2, 2, 2, and then finally you have 3. Okay, so total 8 characters, and these are the frequencies when we arrange them in the ascending order. Okay, so in the first step, we will arrange in the ascending order frequency and merge the first two. In fact, in every step, what we need to do, arrange the characters or arrange the symbols in the increasing order of the frequencies and merge the first two. Now, what do you mean by merging first two? Now, here, what we can see, the first two characters are having the frequency of 1 and 1. Okay. So what we'll be doing, we'll be merging these two. And how we'll be merging these two? See, finally, we need to create a Huffman tree. So in every step, basically, we'll be creating a subtree. I repeat, we'll be creating a subtree. It's an example of a binary tree, or it's an application of a binary tree. And for binary tree, we understand that every node can have maximum 2 children. Every node can have maximum 2 children. So it means that I will be creating a subtree, and how I will be merging these two, that I will be having a root node, and then the first character will become the left child of this root node having a frequency of 1, and then this second character will become the right child of this root node having its frequency, that is 1. And then the addition of these two frequencies, that is 1 and 1, that will become the frequency of the root node. So 2. Okay, so 2 comes there. Fine. And now when I create a subtree, this is the part of the first step. So I get a root node as 2. Then on the left hand side, or the left child of this root node, is the first symbol having a frequency 1. And then on the right side of this root node, I am having the right child, which is the second symbol, and it is having a frequency of again 1. Okay, so this is my first step. This is my first step. Arrange the symbols or the characters in the increasing order of their frequencies and merge the first two. How to merge the first two? Create a subtree. Okay, make a root node, make the first symbol as the left child, make the second symbol as the right child, and then the summation or the addition of the frequencies of the two children will become the frequency of the root node. So 1 plus 1 is 2. Okay, so this is our first step. Let me remove all this. So this is our first step. Is it understood to all? Now we move to the second step. In second step, what's happening? Please see here carefully. What we have done, we have merged these first two. Okay. Now when we have merged these first two, so what do we have with us? What do we have with us? We have this set of frequencies, and this subtree. We have that remaining set of frequencies 1, 1, 2, 2, 2, 3, and then this subtree. Now this subtree is a part of our data. This subtree is a part of our data. So this subtree will go into our list. Which list? 1, 1, 2, 2, 2, 3. Okay, and then in the second step we will sort or will arrange the elements of this list in the increasing order of their frequencies. So this is my second step, and in second step, see here carefully what we have done. We have arranged those all characters or those symbols in the increasing order of their frequencies. So what I have these two ones first of all, okay, over here, and then after these two ones, I'm taking these two, or you can say I'm taking this subtree, because this is also a part of my data. So I'm taking this subtree, and then the remaining 2, 2, 2, 2, 3. Okay, so this way now I have sorted my data. Now you can say that when you have same 2, 2, 2, though, so this subtree could have become could have come after the last two. Means after this 1, 1, we could have this 2, 2, 2, and then after this 2, 2, 2, we could have this subtree. That is also fine, perfectly fine, no issues for that at all. But what I'm doing, I'm just making a common practice that whenever subtree is occurring and I have a symbol with the same frequency as that of the root node of the subtree, so I'm just pushing my subtree before. Okay, so the subtree is coming before. That's all. Nothing special about it. You can do either way, but follow the single way or the single technique. So this way, our input has been arranged. Now, once we have arranged this input, again the same thing. Merge the first two. Now, when I say merge the first two, so in this case, my first two are basically these two, 1 and 1. So I shall be merging this first two. When I merge this first two, so I create a subtree in the same way. So I am having a root node having a value which is equivalent to the sum of the values of the left child and the right child. My left child is going to have a value of 1. The right child is going to have a value of 1. So 1 plus 1 is 2. So this is my left child and this is my right child. Okay. So we have merged the first two symbols and this subtree we have created. Now in the third step, when we move to the third step, you need to understand what we have for the third step. Okay, for the third step, if you see carefully, so we have this. Okay, we have this a subtree 2, 1, 1, then 2, 2, 2, 3, and this newly created subtree. So basically now we have two subtrees, and interestingly those two subtrees are identical. Okay, root node having a value 2 and then two children each having a value 1, 1, 1, and then we have 2, 2, 2 and 3. Okay, so this now becomes the elements or the symbols of our list, and in the third step we will be arranging these elements or these symbols in the ascending order of their frequencies. Okay, so we move to the third step, and in the third step what we are seeing, we are again seeing that we have arranged those symbols. I go back, I show you this again, and now what we can see, into a list we have two subtrees having the root node values 2, 2, and then we have four symbols 2, 2, 2 and 3. So this all symbols we will be sorting and arranging in the increasing order of the frequency in the next step, and that's what we are doing here. Okay, so if you see again what I am doing, I am pushing the subtrees ahead of my other non-subtree values. So I have two subtrees 2, 2, 1, 1, 1, 1, and then four symbols 2, 2, 2, 3. So this is my third step, part of the third step. The second step, the second part of the third step is remaining, that I need to merge the first two symbols. Now, interestingly, into this list, the first two symbols are themselves the subtree. This is my one subtree, the first symbol, and this is my second subtree, the second symbol. Okay, so we'll be merging these two. So merging these two subtrees and creating a subtree, and that subtree will be having a root node which is equivalent, which is having a value equal to the addition of the values of the left child and right child. Okay, so the first subtree becomes the left child. So my addition is 4. The first tree becomes the left child like this. The second subtree becomes the right child, and now this is my newly created subtree. Okay, so the root node value is 4, left child is 2, right child is 2. The left child again has 2 children, 1, 1. The right child again has 2 children, 1, 1. Okay, so this is my third step. When I move to the first step, what do we have as an input for the fourth step? In the fourth step, you have this symbol having this value 2, 2, 2, 3, 4, and this subtree. And this subtree. Okay, so in the fourth step, I need to arrange these symbols along with this subtree in the increasing order of their frequencies. So what we'll be having? 2, 2, 2, 3, and then the subtree having a value 4. Whenever we push, we need to only see the value of its root node. We only need to see the frequency of the root. Okay, so this is my fourth step, and these are the sorted list of my fourth step. Okay, now when the sorted list in the increasing order or in the ascending order of the frequency has been written here, again what I need to do, merge the first two. So now we'll be merging these two symbols having the value 2, 2. Okay, and we'll be creating a subtree out of it. So this way a subtree is created. Okay, and now we'll be going into the fifth step, and into the fifth step, what are the inputs to be arranged in the ascending order? These are the inputs which has to be arranged in the ascending order. The two subtrees and the two symbols. Okay, so when we arrange in the ascending order, what we will be getting? 2, 2, and then this already a bigger subtree having a root node value 4, and then the newly created subtree, this one again having a value of 4. Okay, so this way we'll be going to the next step, step number 5, and in the step number 5 we have the sorted elements like this. Okay, and now we'll be merging the first two, and when I say I'm merging the first two, so in this case the first two symbols to be merged are 2 and 3. So we'll be creating a subtree having a value 5, because 2 plus 3 is 5, left child is 2 and the right child is 3. Okay, and then we go to the sixth step. When we go to the sixth step, what is the input for the sixth step? For the sixth step, the input is all subtrees. This is the input. So my first subtree is having this value 4, my second subtree is having this value 4, and my third subtree is having this value 5. So I will be arranging these subtrees in the increasing order of frequencies, exactly like this, only 4, 4, 5. So that is our next step, and it is step number 6. Okay, so now they have been arranged. Now when we have arranged this, what we need to do? Merge the first two. Now here you already have the first two. This is my first symbol, I can say, and this is my second symbol. So basically I will be merging this first two. Okay, I will be merging the first two, and I will be creating a subtree out of it. So it will be having a value 8, because 4 plus 4 is 8, and then the subtree will follow down. Okay, so it will follow down, it will come down. I have not drawn here, that you can understand. Then we move to the next step. our step number 7. Now in step number 7, what is the input? For step number 7, the input is basically consisting of this subtree having a value 5 and this newly created subtree having this value 8. Okay, so basically the first value is this subtree having a root node value 5 and then the second subtree having a value 8. Okay, so that becomes the input. So my first symbol will be subtree having a root node value 5. Second symbol would be a subtree having a root node value 8. So that is my step number 7. Okay, so these are the inputs, and they should be in the ascending order. So I just made a mistake over here. That mistake will not change the output drastically, but it is a mistake. So subtree having a value 5 should come first, and a subtree having a value 8 should come next. So basically this should come first and this should come second, and then accordingly tree should be created. So in the next step, basically what we'll be doing, we'll be merging these two, and we'll be creating a final tree, and that final tree will be having a root node value as 13. And the left child should be 5 and the right child should be 8. But unfortunately a mistake has been done over here, and the left child I have just taken that 8 as the left child and 5 as the right child, and then finally a tree has been created like this. Having a root node value is 30. Okay, and this tree is called as a Huffman tree. Then what we need to do, that change you can do, that will not affect your output drastically, because what is important, the length of the characters are important, which would remain same. Okay, whether it is a right child or a left child, that doesn't matter much, but I request you to change it, and while providing you this as a material, I will check. Now, what we need to do, we need to assign the weight or the value to each edge of a tree. I repeat, we need to assign a value or a weight to each edge. And it is quite simple and straightforward. A left edge will have a value of 0 and right edge will have a value of 1. Okay, a left edge is having a value of 0 and a right edge will have a value of 1. So I will be starting with the root node. My root node is 13 over here, which I can see. So this is my root node having a value 13, and this is my left edge of the root node, and this is my right edge. Okay, so the left edge is having a value of 0 and the right edge is having a value of 1, and this way you need to give value to all the edges. Okay, so then I come down to this 8, and then I give a value to the left edge of 8. This is my left edge of 8, and this is my right edge of 8. So the left edge will be having 0, right edge will be having 1. Likewise, I go to another root node, say 5. I come to 5, and I assign a value to its left edge and right edge as 0, 1. Then I go to another node, assign a value 0, 1. Then I go to another node, then I assign the value to its edges 0, 1, then 0, 1, and then 0, 1. Okay, so this way all the edges now have been assigned the value or the weight. Once these values or weights are assigned, then what we need to do, we need to now label the leaf nodes. All the leaf nodes which you can see over here, this leaf node, this leaf node, all these leaf nodes will be having some label. Those labels are nothing but the characters. So in short, every leaf node represents one character. I repeat, every leaf node represents one character. If you remember, so we had total 8 unique characters. So we must have 8 leaf nodes into our Huffman tree. So if you count here, so 1, 2, 3, 4, 5, 6, 7, 8. Okay. So we have 8 leaf nodes. Each leaf will be representing one character, unique character. And the value of the leaf will represent the frequency of that character. I repeat, the value of the leaf will represent the frequency of the character. Okay. So the first character was D, having a value or the frequency of 1. So this is my first leaf node which is having a frequency of 1. So what I need to do, I start from the left side, for example. So I start from say this side, and I just see, okay, bhai, what is the frequency of the leaf node. Then I go to my characters list. I see which is the first character which is having that frequency, and I just label this leaf node with that character value. So I label this leaf node with that character value as D. Likewise, I go to the second leaf node. I check its frequency. The frequency is 1, and likewise I go to my list of characters. There I see the character with the frequency 1, and I find that S is that character, so I label this as S. Likewise, I will be labeling the next leaf node, then the next leaf node, then the next leaf node is having a frequency of 2, and which is my character A. Then the next leaf node is having a frequency of 2, which is my character R. Then the next leaf node U, and then the next leaf node having a value 3. So that is my character T, which is having a frequency 3. So this way I have labeled all the leaf nodes. This way we have labeled all the leaf nodes. Okay. Once all leaf nodes are labeled, now you can find the varying length code. What I need to do to find the varying length code? To find the varying length code, I need to see the character. So this is my character D. If I need to find the varying length code of D, I need to start from the root node. For every character's varying length, I need to start from the root node, and I need to follow the path. So I need to start from the root node and I need to go to D. So this is my path. Along this path, whichever bits are coming, so 0, 0, 0, 0. This is the varying length of D. Likewise, the varying length of S. I need to find the varying length of S. We'll go with a different color. I need to find the varying length of S. So the varying length of S, I need to start from my root node. I need to follow the path. Along the path, whatever bits I am getting. So 0, 0, 0, 1. That is the varying length of S. Likewise for all the characters. For C, it is 0, 0, 1, 0. For E, it is 0, 0, 1, 1. For A, if you see for A, so for A, it is 0, 1, 0. For R, it is 0, 1, 1. For U, it is 1, 0. And for T, if you see it for T, so it is 1, 1. Okay. So now we can see that different characters are having different length codes. The length of the codes are different. Okay. And then finally, we go back to our original table, and into that table, then we specify the varying length code. For D, it is 0, 0, 0. Then for A, it is 0, 1, 0. For T, it is 1, 1. For S, it is 0, 0, 1, and so on. And then if I find out the total number of bits using that varying length, so it is coming out to be 26. It's coming out to be 26. Okay. And as I said you that I made one mistake, and that mistake is what? That this subtree should be the left child, and this subtree should be the right child of my loop. So you please do that. You do those changes, and I repeat, the length of the codes will not be changing. Only the value of the code will be changing. Okay. So that's not a big deal. For example, in case of D, it would become 1000. Instead of 0000, it would become 1000. Okay. So only the codes would be changing, but the length of the code would not be changing. And we are worried, or we are concerned for the length of the codes, because that way only we'll be compressing. That way only we'll be reducing the size of the overall data. Okay, so please make that changes, and then you finally create this table. And once you create this table, then your problem is solved. Okay, so this is your Huffman tree, and while you traverse the Huffman tree, for every character you will find the varying length code. Okay, so this is how Huffman tree helps us reducing the space requirement of the data by assigning variable length code to different characters, and that variable length code depends upon the frequency of the character. Depends upon the frequency of the character. Okay, so any query from your side? Stopping the recording.